Well, good afternoon, food science foodies. So recently I did a presentation on gluten and really asking this question, why is gluten in so many foods? So today I'm going to give you a version of this presentation. So, why is gluten in so many foods? Gluten is in a variety of foods ranging from breads, cakes, and cookies to pasta and crackers and so many of our snacks. So, from a food science perspective, why is gluten in so many of these foods and what role does it play? So, in order to answer this question, first we have to go into the anatomy of a grain or kernel of wheat. So when we look at this slide here, you can see that a kernel of wheat consists of the exterior bran, which is commonly sold in stores as fiber. It's not digestible, but again, great for fiber. The endosperm and the germ. Now the germ is the portion that will grow to become a new wheat, the actual plant. The endosperm is the part that we commonly call the flour. So it consists of about 70 to 90% of the kernel. It just depends on the variety. Obviously there's going to be variation between plants and the type of wheat that you're growing. But this endosperm is very important because, as I just mentioned, it's what we call flour, and it contains the majority of the nutrients that we use. So it contains starches and proteins, and importantly, it contains the two proteins that go on to form gluten. So those two proteins are glutenin and gliadin. So first of all, I want you to look at this structure here of glutenin. This is a suggested 3D model, and you can see that it actually has multiple subunits, high molecular weight and low molecular weight. So we're just going to kind of do a surface overview of this, but this is glutenin and this is gliadin. Now both of these are present in a kernel of wheat, but it is not gluten. So a kernel of wheat does not actually have gluten, but it contains the necessary ingredients to make gluten. So, how do these become gluten? Well, gluten is formed when we have gliadin and glutenin in the presence of water, and then you add shear force to that. So, you can kind of see in this simplified diagram that there's glutenin, water, and gliadin, and once they interlink, once the water's there to allow them to connect to each other, they form this network. And here's an example of just kneading some dough, and this is exactly why we need bread dough, because we want to create the gluten network and that structure that's going to be key to the characteristics of bread. So we'll get into that a little bit more later. Now, moving on to the question, why is gluten in so many foods? So, from a food science perspective, when we look at proteins, we usually will look at what we call food functional properties. Now, the main three of those are going to be foaming properties, foaming capacity. So you can think of whipped cream. So the ability of a protein to basically hold an emulsion of air in a liquid, such as whipped cream. Gelling capacity, so the ability of a protein to form a network and then trap water in that network, and that's essentially what a gel is. Think of Jell-O. And lastly, the ability of a protein to stabilize an emulsion. So an emulsion is two immiscible solutions, so water and oil. You mix them together and naturally they're going to separate out. But if you have an emulsifier, which many proteins act as, then it actually holds those two together. So it'll act as a mediator, you could think of, between the oil and the water, and it links them together. So you can think of salad dressings that you've seen in the store, where some of them don't contain emulsifiers, and you'll see that they're separated, and some that do contain emulsifiers, and that is part of the reason why they're not separating out. So the unique characteristic that gluten brings to food is that it is uniquely elastic and strong simultaneously. Now that is a hard thing to find and a hard thing to substitute for. Because of that unique ability, we're able to do things like form breads, which you have the rising of the bread that's due to either oxygen or CO2, and basically what happens is the gluten network that you form catches all of that CO2 or all of that air, and as it bakes, it rises and it sets, and when the protein sets, you have those nice air pockets that are formed, right? So it's strong, and then it's able to withstand the rising, and it's elastic, it's able to rise up and not break. So that's the unique property of gluten. Now that's also the reason that you can make pasta and you can roll it out really thin and still have a good sheet of pasta that's not tearing or breaking. So here's just an example that I'm about to show you of the difference between a cake flour and a bread flour. So as it turns out, the difference between cake flour and bread flour is the amount of protein that's in the wheat kernel. See, lower amounts of protein are better for a cake. So when it comes to cake flours, we want to have a low amount of gluten because that's going to allow for us to have that soft, melt in your mouth kind of texture. Whereas with bread, we usually want something that's got a little bit more bite, more chew, and able to withstand the rising, which gluten is key to. So here's an example here of, first we have the bread flour, and you can see that it's more elastic, stretchy. And then we have cake flour, which was not as malleable, not as stretchable, because it contains less gluten, and therefore there's more starch to gluten ratio. So with that also being said, another way to think of this is, as a food scientist, we are building a food, right? So an engineer is going to build a house. They'll look at their building materials and they'll have brick, concrete. There are tons of different kinds of concrete, different types of brick, wood, and all sorts of building materials. So when we want to build a food, we have to think of the end product first. What do we want this food to behave like? Do we want it to be able to rise? Do we want it to be fluffy and chewy? Do we want it to be soft, melt in your mouth? How do we want the end texture to be? How do we want the end flavors to be? And when it comes to that, gluten is a unique building material because of that strength and elasticity. So when we look at that, it's kind of it's used in so many foods because of its versatility and its unique abilities. So in conclusion, gluten consists of two proteins, glutenin and gliadin. It forms in the presence of water and with shear. It possesses unique functional properties, namely the strength and elasticity. And gluten is an ideal candidate for building the structure of many of our foods. And that's why you see it in so many of the foods. So with that being said, I hope that this helps you better understand why gluten is present in so many foods. And even further, why it's hard to replace gluten in so many foods. In fact, on that note, it's because of those unique properties that are so hard to emulate with other proteins that gluten is still so prevalent, and why you might have had a gluten-free bread that was made with rice flour but tasted completely different, had a completely different texture. So the problem has not been solved yet, if you will, for those who have gluten intolerance. We don't have a great substitute just yet. That's the problem. But there are scientists working on trying to mimic those functional properties using other proteins. So there's no solution if you have a gluten intolerance now, but if you don't have a gluten intolerance, then enjoy the variety that is because of gluten. Thank you so much for watching. If you like this video, please hit the like button. Please subscribe. There'll be lots more content coming. And if you have any questions, leave them in the comment below. Let me know what topics you'd like me to tackle next. And have a great day.
The Food Science Foodie.